Okay, even though we've gone ahead and built up this relationship connecting the Jones and Mueller matrices, Jones and Mueller tensors, we're going to take a step back now and just think very generally about the Mueller tensor and how we can potentially take advantage of tricks to simplify it that do not require us to assume or relate it back to just the purely polarized component through the Jones framework. So now this is just a Mueller, a model-independent Mueller-only simplification. And it turns out that that symmetry can work to our benefit in reducing the total number of non-zero elements that have to be considered in the Mueller tensor. So the objectives here today are in this section are just to see how that plays out in terms of considering particular symmetry relationships. And we're going to focus on one symmetry in particular simply because of its ubiquity, but hopefully you'll see that the approach taken to describe the symmetry properties could be easily generalized and applied to arbitrary symmetry relationships. But uniaxial set symmetry and effective local mirror plane symmetry shows up routinely in biological imaging where you have a lot of polarization, purity, depolarization arising. So it seemed like a good place to start, a pretty common motif in terms of structural characterization in biological tissues, for example. And in a uniaxial surface, you might have, for example, if you're a membrane, you're going to have effective mirror plane symmetry about this axis. And if you're a fiber, effective mirror plane symmetry about the long axis. So those are the symmetry axes that we will be considering in this illustrative example of local uniaxial symmetry. Why do this? Because if there is the presence of symmetry, then that's going to reduce the total number of Mueller tensor elements that are symmetry allowed. If we can reduce the number of tensor elements that are symmetry allowed, then we don't have to solve for as many when we invert the system and describe and recover those Mueller tensor elements. So that's really the key advantage, is simplicity afforded through the presence of symmetry. So let's consider this case of a uniaxial system and ask how, first, before we think about Stokes and Mueller, let's just consider what happens with Jones tensors. So if I had a Jones tensor in the local H prime V prime reference frame, where H prime parallels the unique axis, and I asked how would this system, how would my Jones vector be affected upon application of mirror plane symmetry, then about the H prime axis, what you'll see is it'll invert the V prime coordinate. And so if you have an electric field written in terms of H prime V prime, if you apply the symmetry operation of the lattice in the local reference frame, you'll have a new Jones vector that looks like this. Now, if the ensemble has this symmetry, then the Mueller tensor or the Jones matrix describing this process should be unaffected by the application of this symmetry operation, and we'll get to that next. But I just want to illustrate, first of all, how we think about these symmetry operations in terms of the Jones vectors, and what that generates is a symmetry operator, in this case corresponding to reflection about the H prime axis, given by this simple 2x2 matrix. And this is where any arbitrary symmetry operator could be placed into that role just as easily. So if we then want to know how is this going to affect a Stokes vector, it turns out there's a really slick way of connecting those, and it's just shown right here. We can calculate what the equivalent symmetry operation is going to be for the Stokes vector. I'm just going to use that by the capital sigma as opposed to the lowercase sigma. By the Kronecker product of the sigmas, and in this case it's a simple, the complex valued part doesn't really matter because we have a purely real valued symmetry operator. And then the reference frame rotation terms that take us from the electric fields back out to the Stokes. So if we use this simple relationship, then that generates a corresponding symmetry operator for a Stokes vector. So if we have mirror plane reflection symmetry in an ensemble, then the Stokes vector, according to that symmetry, will invert in the 2 and 3 entries and stay unchanged in the 0 and 1 entries. And if we think about that, does that make sense? I certainly hope it does. So now the new Stokes vector is just going to be related to the old Stokes vector multiplied by the symmetry operator, now applied in terms of the Stokes reference frame. Now, the advantage of doing this is not just for describing the Stokes vector, because that's actually pretty straightforward. What we really want to do is use these symmetry operators for manipulating and understanding what's going on in terms of the Mueller tensor. And in the framework that we had before, we can sort of see, perhaps it's obvious to you, perhaps it's not, but what we will end up doing when we take these symmetry operators and applying all of them, we will end up with our new local frame, indicated by the lowercase little l. The local frame Mueller tensor is going to be the local frame Mueller tensor that we started with, and then multiplied by these symmetry operators on both the right side and the left side. And that will tell us how the symmetry operations affect the new Mueller tensor. If there are elements in the Mueller tensor that invert in sign, for example, upon application of the symmetry, then those must be zero valued, because M must be unchanged by operation of this symmetry if it has that symmetry. So that's how you can tease out which of these are relevant, which one of them are, which tensor elements are retained and which ones are lost based on this symmetry. So in practice, and we'll say more about vectorization later on, so feel free to jump forward and jump back again, but in practice it's easier to evaluate which of these tensor elements are non-zero valued by vectorizing the Mueller tensor first. But that's really just a case of practicality. It doesn't really affect the overall outcomes that I'll be describing here. Okay, so we're going to use two combined symmetry operations to simplify the Mueller tensor. One of them I haven't even really mentioned. We're just going to implicitly assume that the right two elements in the Mueller tensor are interchangeable. And that makes a heck of a lot of sense because, I don't have it written down here, because the Mueller tensor connects the Stokes for the sum and if we have to S, let's call this 2 omega. We'll go ahead and make that 2 omega. So if we're doing second harmonic generation, in the case of second harmonic generation, these two elements are identical. The two Stokes input vectors are identical, and so therefore the rightmost two indices in the Mueller matrix, the Mueller tensor, must be interchangeable as well. So that reduces the number from 64 possible non-zero unique tensor elements in the Mueller tensor down to 40. We can cut that in half again by using the mirror plane symmetry operation. And what you do, once you apply that symmetry operation, these are the full set of all of the tensor elements that survive. And you can see that there's only 20 unique ones because there are a number of equalities that connect these. You can see that in this case it's pretty obvious that the origin of this equality is simply the interchangeability of the rightmost two indices. So that's a pretty big savings. We've gone from 64 possible, 40 in the general case of second harmonic generation, down to just 20 symmetry allowed elements through the application of local frame symmetry. So that's why there's a big advantage to considering symmetry. This is just one symmetry operation, a mirror plane reflection, but you can, of course, adapt this for, if you have a crystal, for example, it'll have different sets of symmetry operators, and the same sorts of rules could apply for manipulating Mueller matrices of those as well as the case that's shown here. So this is a very, very general framework, just illustrated with a common case for uniaxial assemblies.